You take over. Okay, everybody, welcome. Thanks for braving the wetness outside. So this might make this a time to talk. It is my pleasure to introduce you to Katherine Kreuser, who is going to talk to us about physical informed storm surge estimation.
Hello, everyone. Just give this a moment to.
Oh, no.
Oh, uh-oh.
Is he giving you a hard time?
No, just give it one moment. Adobe, we might need to, oh, no, that's not right.
Yours is called Math Club presentation.
Well, no, this is mine, though.
Here, let me, it needs to be downloads. My phone. Oh, I think that's not right.
There's always something like this. I have that effect on technology.
There.
Okay,
That's it right
everything
there. Okay, so that's it. Right there.
Yes. So let's open up Adobe. See if they'll let us do a presentation.
What you see though?
Let's see.
You have to do that in some classrooms every single day. You might, I think you have to actually go into the, gotta go back to the previous screen. If you click institution, it should work.
Over here.
Yeah, click.
Did this happen last semester?
Oh, yeah. In certain classrooms, it would happen every single. Open it again.
Okay, I'll close it and open it up again.
So,
I just wanted to stop forward.
There's going to be open up PDF.
So it's on the side.
So, okay, so scroll down.
Few more.
Yeah, view more. It might just be.
Oh.
Yeah, talk about that.
No, I don't eat that. I don't eat that.
It's strong.
So I don't use my G.com now, but it might work.
I didn't believe it's like. That is what it is. I can tell.
So let's try this.
And it goes like, well, and then the chart. But I haven't eaten it. Okay, wait, you're in a distance. This is good.
No.
I think you're so.
So I have to sign into view PDFs every once in a while, and like I always use my cousin account, never my G.com. I don't know if that makes a difference.
Okay, that's not working.
It's not looking cool. It's one good.
Let's try. From my personal email, see if that works. Oh wait, you said
Try
that without G.
Without the G, no.
Yes,
Don't click Google either, just log in normally.
okay. Isn't this open?
We not just tell CCIP that like it's a PDF, but it's like. Yeah, so just type your email address in there. They used to not be able to like save changes to this stuff, but we can't do this, impossible, that COVID hit and they basically, when we came back, they forced to.
No.
Yeah, absolutely.
Let's see, well, it worked.
Yep.
Okay, now it's just. How do I do presentation?
View. Up at the top. Further up.
Oh, yes. You.
Full screen.
Okay, that works. Okay, now we're ready to start. Okay. Apologies for the technical delay. So today I'm going to do something called physical informed RU return level estimation. So specifically what my project focuses is on is storm surges. However, I want to stress that this are what we do mathematically can be applied to many different things. So for instance, I've seen something kind of similar to what we've done, but not quite applies to even volcanoes and lava flows. But for this particular one, I'm focused on storm surges. So one of the questions I get often is, what is a storm surge? Well, when a hurricane like this gets close to shore, the winds blow on the ocean and cause these abnormally large waves, which cause flooding. Now, these are extremely destructive. Here's an image of of destruction caused by storm surges. And in fact, they are the #1 cause of hurricane-related deaths. So because of their intense potential for destruction, we really want to estimate and model them. So in particular, FEMA and the US NRC are interested in predicting storm surges, and particularly high ones. So FEMA is interested in this for evacuation purposes and for infrastructure building, and the US NRC wants to do it such that their coastal nuclear plants can withstand very extreme floods. Because you don't want your regular hurricane to come in and knock your power plant down. So I've been saying RU return level. What is that? So how many of you have heard of something like a 10-year storm or a 100-year storm? Raise your hand. So one thing that you might notice is it seems we get a 10-year storm maybe close together without 10 years. Like, hey, I got a 10-year storm 2 years ago. What's up with that? That's because we say that in our year, or 10-year or 100-year, is the magnitude of events that's expected to occur once every R years on average. So that means you would it's binomial distribution. If some of you guys are familiar with that, probability associated with it. So for instance, a 10-year storm we would expect to see on average once every 10 years, but it's not uncommon to see it once every 2 in 10 years. But you might be thinking also, well, what about climate change? You know, climate's changing, so looking 20 years in the future. Well, how we deal with that is we consider RU return levels that change through time. So an RU return of a 10-year storm today might be different than an RU 10-year storm 20 years from now. So we know what we'd like to estimate RU return level. How do we do that? How do we estimate it? Well, normally how we do it is you estimate a CDF and then estimate this line right here such that this area is equal to 1/r. Problem is, how you can do that is, for instance, if you have data, you can plot the histogram and then brute force find the line such that this area is approximately equal to 1/r. Problem, for storm surges, we often don't have a lot of this data, particularly if you're looking at a location, a storm surge location, where you don't have a particular device for measuring. These devices that they use for measuring storm surges are actually very sparse. I'm sure. Next slide. So over here, these red areas are where they accurately measure storm surges. So for instance, if you're interested in what about a city right here, you can't accurately measure storm surge. So we know we have a problem. What kind of data do we have that can maybe apply to the problem? So we have hurricanes have this input-output relationship. So there's the input, that's stuff like how big is the storm, how fast is it, where is it going, that can tell us some things about the storm surge output. Now, this input, these hurricane characteristics are limited but well observed. Hurricanes are still considered rare events, but thanks to satellite imagery, they are well observed. So we can more easily measure a hurricane, how big it is, how fast it's going, those sort of things. So what about the outputs? That is the storm surges themselves. Well, they're limited in space and time. So how are we going to remedy that? It's something called a computer experiment. That's where it's this complex computer code made by experts, where you plug in your inputs, hurricane characteristics, and it spits out what it thinks the storm surge will be at many different locations. So over here, I've got an example. This is zoomed in on Florida. It says if a hurricane lands here, it has certain speed, certain the size. Then this is what it thinks the storm surges will be at all these different areas. Further on, I've got Charleston indicated here. There's only 10 storms, or it might be something like 8 storms that make it within 10 kilometers of Charleston since 1950. So if you're interested in storm surges at that area, you're not gonna have a lot of data. Okay. So here's how we're gonna break down the problem. We're gonna break down the problem into 3 steps. The first step is we're gonna estimate the input PDF of our inputs. So that's the hurricane characteristics. So step 1 is get an estimated PDF of the input characteristics. Step 2, estimate the input-output relationship. Here I've got a one-dimensional example. Step 3 is get observations from this PDF and plug them in to the estimated input-output relationship. So now what we can do is we can look at this axis and get a PDF of just the outputs. Then we can do that thing that we did that was on a previous slide for our year return level estimation. So we're doing this kind of a roundabout way, but we're going to basically kind of, we call it simulate this output, because you're using your input-output relationship, plugging things in, and then you have your PDF. So here's it a little bit more mathematically, the 3 steps. So the input, we have the hurricane characteristics, records are more complete. And we're going to use this as inputs to simulate storm surge levels. So this task for this part is estimating the input PDF. Second step is the model, input-output relationship. How we're going to do this is we're going to simulate high-fidelity storm surge response. What that means is we're going to use existing complex computer code, plug it in some X, and it will give us Y's. But the problem is that's computationally expensive. So I'm going to go a little bit more about how we do a mathematical surrogate around that. And then the last thing is combining things, where we're going to get simulations from these input PDF, plug them in to the estimated input-output relationship, and it will give us many different outputs, which we can use to estimate the RU return level. So I've said computer experiment earlier, but what is the exact definition? Well, the computer experiment consists of running deterministic computer code, various input configurations to obtain corresponding outputs. Now, this is often made by experts at the problem, and it uses complicated differential equations made by using different physical things like still water equations made by experts on the physics behind storm surges. Problem is, this computer code, it's a very long time to run, like need supercomputers working on it for hours, and input-output relationship. So what we are going to do is we use the computer model called ADCIRC, and we were given, thankfully by UNC, 3,156 different input outputs. So 3,156 X's and the corresponding outputs. And the outputs were for many different locations. So specifically, there's something like 118,000 different locations. For illustrative purposes, though, we're not going to focus on all those locations. We're just going to focus on one output location, which is located near a particular state park. It's around this area. Eventually, we'd like to extend our method to many different locations, but for now, for illustrative purposes, we're just focusing on one. So, how we're going to get around the computing problem for the computer experiment is we're going to use something called a surrogate model. So what that is, it's kind of a stochastic process that you use to in place of the deterministic function. So this is the graphical example I would like to use. Let's say that this black line is the true input-output estimation that you want to see. Might be a little bit hard to see at the back there, but there's a black line right there. In reality, you don't see that. You would like to estimate. What you do see are these black dots, these observations. What you assume with this particular surrogate model is you assume that the closer these points are on the x-axis, the y values are probably also going to be similar. And that assumes similarity, but you can use to get an estimated distribution along the confidence intervals. Now, ideally, what you would like is you want the surrogate model to be able to get predictions, given data, and you'd like to be faster than putting it into the computer model. So something called a Gaussian process satisfies all these requirements. And in fact, this is an example of a Gaussian process fit. So what is a Gaussian process? So it's essentially an assumption that for any finite inputs, outputs are multivariate normal, which sounds like a very broad generalization, but it has some very powerful aspects to it. Generally, it's governed by two major things: its mean function and its covariance function. Now, it turns out the mean function actually isn't that important. What's truly important is the covariance function, which says how likely are two outputs going to be given you know how far away their inputs are. And it's usually governed by something called a kernel. Now, there are many different types of kernels. One of the very most common ones is called a return, where usually you have two main parameters. You've got sigma squared, which is the variance, but the main important ones are nu and growth. So don't pay attention to this one over here. This is called something a modified Bessel function. You don't have to worry about it for now. Focus on nu and rho. So normally what happens is nu governs the smoothness of the Gaussian process. So normally what you do is you look at your data, you do some different statistics, and you choose what you think the smoothness should be. Then you can estimate rho via things like maximum likelihood estimation, or whatever estimation you want to do. So here's an example. Here are different covariance functions with different nus, and here there is some examples of the Gaussian processes they make. So even though these covariance functions are very similar, they can cause very different looking Gaussian processes, and they affect the smoothness. So I mention this because it's very common in the world of computer experiments to use Gaussian processes, but to only use one covariance function. That might not work for your data. So for instance, if you have an input-output relationship that's very smooth, and you use this spiky one, you might get confidence intervals that are unrealistic. So the next is our results. So what we do is we actually do multiple covariance and see which gives us the best fit. We lock transform our output and lock transform particular inputs. We also assume something called a separable covariance function. That's where you assume the covariance function is a product of all the different categories of inputs. So because we have multiple categories of inputs, that's things like speed, size, the covariance function is going to be a product of a covariance function applied to each one. So that is the covariance for everything is the covariance of the speed times the covariance of the size versus the covariance of the angle of heading. We're going to use NRMSPE. You don't have to worry about it too much. The main thing to know is that you can treat 1 minus NRMSPE kind of like R squared. Closer it is to 0, the worse the model is. Closer it is to 1, the better. If you end up with a negative values, it's not horribly wrong. We also split our data into 75-25 split. This is actually very, very generous. Gaussian processes are nice in that you can still get good fits even with something like training having only 33% of the data. But for now, we just did 75-25. And here's a table with some more results as well as the plot. Here on this plot, this x-axis is the testing data of storm surges, and the y-axis is prediction. So the model does better the closer these dots are to this line. So what you can kind of see is all models do pretty well down over here, but up here is when they start to get worse. Now, you might ask, why not just look at these? Well, because these over here, I have actually filtered the data. This starts at 2 meters. And 2 meter storm surge can still be extremely disruptive. So that can really mislead us if you don't put it in the model. Now what this over here, it means is that I've looked at different covariance functions and looked at how good it is. Now the general result is that the this one where nu is 0.5 and this one where nu is 1.5 tend to do the best. And in particular, it might be difficult to see, but you can kind of see this number 2 and number 3 tend to be closer to the line up here versus number 4, which does worse. Now, this is particularly helpful because in the world of computer experiments, oftentimes people just look at this one, this covariance function, and then if they say, oh, the model's bad, you can't use Gaussian process. Truth is, you can put some other covariances. So some of you might ask, well, you've only looked at one output location. Maybe it's not true for everyone. So what we did is we did a little side experiment where we looked at 1,000 different output locations in a small subregion of west coast of Florida, and that did the same process and said, do these results still hold? And here's what we found. This is the average in our MSP. Again, closer to 1 better, closer to 0 worse. Exponential and return with 1.5, so be better. Over here, what this means is this is the proportion of areas where this one was the best. So 46.5% of the areas had the best option as exponential, 33 had return, and squared exponential was only 3.7%. So, and I also took a chance to look at these areas where it's doing better, and the areas where it does the best, everything's doing bad. It's just the best and bad ones. So this pattern does hold for multiple locations. It looks like these two covariance functions are probably going to be the best bet. So what that was is we just went over this step, this middle part. Now we're going to go over this part where it's the estimating the input PDF, which is I've included secondly because it's a little bit less interesting. So our data source is we use something called IPTrax. It has best tropical cyclone data for all the way to 1951. However, we do not trust the data before 1950. Why? Because that was before satellites. So the first thing we do is we filter out the data so that we're only looking at things after 1950. So there are these particular hurricane characteristics that we're interested in. What is the pressure deficit? Difference between the pressure at the center of a hurricane and the general atmospheric pressure. So that says how strong the hurricane is. Radius to max wind speed, that's how big it is. Forward speed, how fast it's going. Heading angle, which direction is it going? Distance from landfall, that's the difference between where it lands over here and where you're interested in the storm surge. So this distance. So we want to estimate the input distribution for each of these. But we have to be careful with dependence. Specifically in the literature, it seems that delta P is the most important one for estimating storm surges. And also there's dependence on the radius versus the pressure. So based on that, we use something called a generalized Pareto distribution for delta P. We do that in particular because that distribution tends to be better at estimating the high tail of the distribution, which is important because high tail delta P's are very strong storms, which make very strong storm surges. We also do this dependence where we look at log normal and log gamma fits for the radius given delta P. Log normal is common in the literature. Log gamma is something we explore that gave us better fits. We also do some general fits for BFF and theta. For theta, we do beta after shading and skipping. For BFF, we do gamma and log normal. So these three are some QQ plots that basically show us some of the different models we fit, why we chose the ones we did. This one is showing the model fits and confidence intervals for delta P versus our radius. So that was let me go back here. That was this fit. So we've done this fit and this fit. Now we need to do this fit. But before I do that, I have to talk a little bit about extreme value analysis. So in the world of ordinary statistics, you want to know about the bulk distribution, and so you have different theory and distribution. You use the central limit theorem, everything ends up coming up normal. But for extreme statistics, you're interested in the tail distribution. So what kind of theory or what kind of distribution are we supposed to use? So this example looks at the sample maximum. So for instance, here's the essential limit theory demonstration. We're gonna generate 100 random numbers, get the sample mean, and repeat. Here you can see the different sample means. And then as time goes on. This should look more and more like a normal distribution. So those of you who are familiar with statistics might be familiar with this. If you look at the PDF of this, it should look like a little bell curve or normal distribution. It's kind of evenly spread around 5. But what about sample maximum? So we're going to do the same thing, but instead of the sample mean, we're going to look at the sample maximum. So here. So, do you guys think it's going to be symmetric, left-tailed, or right-tailed? How this is looking?
Right.
Yes, right-tailed. And in fact, the name of the distribution that it gets close to is of this form. So this is some math. So if that's your maximum, Mn is the maximum of n random variables with their IID. And if there exists certain constants, such that as n goes to infinity, that is true, then G has to be in this form. It's called the generalized extreme value distribution. The important parameters are mu, sigma, and z. The z variable controls the shape, how heavy the tail is. And then there's also another distribution. So if you have the maximum, sample maximum, then for a large enough U, this probability is going to, and this probability is going to be well approximated by the generalized Pareto distribution over here, where you've got sigma tau c and mu. So I mentioned this because of the method we're going to be using actually is going to use this distribution instead of the generalized extreme value distribution. So why is that? Well, there's two major tools that we use in extreme value analysis. One is something called block maximum. Let's say you pick a block size, let's say a year, and you look at the maximum of your data for that year. Then you go to the next year and you look at the maximum of that, so on and so forth. Now that works if you have highly regular data and you have a lot of it. So things like rainfall, that makes sense. It rains a lot during the year. But for storm surges, it doesn't necessarily work because you might have only one hurricane landfall nearby your outlet. And in that case, the maximum for the year is just that value. Or you might have no hurricanes, or you might have just one hurricane. It is possible to have two, but this block maximum method works best when there are many different data points within the block. So that method would just be looking, barely filtering the data at all, just looking at the health distribution rather than scale. A different method that's a little bit less commonly used, but still useful, is called the peak over threshold method, where you pick a threshold and then look at the data that's above that threshold. And you say that's going to be the tail data. So this is going to be a better fit for us because our data is sparse in time and irregular. So the big thing to note is that this distribution, for reasonably large U, the data should be close to a generalized Pareto distribution. This blue circle data. So here's the current plan. We're going to use something called the Monte Carlo approach. What that means is we're going to, instead of doing these things theoretically, we're going to do them via computers and coding and then see what happens. So Step one, simulate a large number, let's say 1,000 storms from that estimated input distribution, PDF. Step two, gets the estimated input output relationship via a Gaussian process fit. Step one is using IB tracks, looking at the satellite data of these hurricane parameters, estimating their input distribution. Step two is plugging them in to the Gaussian process fit. Step three is choosing a reasonable threshold U for to do the GPD, generalized burrito. Step four is you can use the GPD fit to estimate the R return level. And in fact, here's an example of someone of one of our numerical experiments to do just that, where you've got these predicted storm surges, you've got a threshold of 1, and you've got the estimated R. So I haven't included all of our work in this in these slides, but there is some things that I've left out for the sake of time and simplicity. We've done a couple different numerical experiments to see the sensitivity of what threshold to choose and that sort of thing. What we'd eventually like to do is do our emulation for more output spaces. And that's because it's probably the case that if two output locations are similar, the same hurricane is probably going to have very similar storm surge levels there. So we can probably make an assumption for how related that is, and then that way we can speed up the model for many different locations. Next is speed up computation. The appeal, one of the appeals of Gaussian processes is that it's faster than ADCIRC, but Gaussian processes can still be a little bit slow. So the faster that you pick, the better. And then refine the model. I've gone over 4 particular covariance functions with severable structure, but there are also different ways to build a covariance structure that we investigate. And then we want to implement FEMA's method so that we can compare ours to theirs. Ideally, we'd like our method to say that we have a more realistic uncertainty of prediction. And then that's it for my presentation. Not sure how I did on time.
Questions?
Yes.
Did you by chance attend the lecture yesterday on physics informed machine learning?
I said there wasn't even.
Okay, well, there's a lot of similar things that you talked about, so I would recommend maybe that you look into that, because specifically Cardiatic is the author has been apparently created like a course that teaches some of the stuff that he works on, which is very closely related to this, but of course more machine learning focused. But there are a lot of very similar things, so it's interesting to see the overlap.
Other questions, yes.
Yes.
So I guess like your approach, like how common is that? Like when you're like talking about like broad like modeling in general, like your approach of doing like statistics stuff versus like just like computational modeling.
So let me go back to this one. So it is very common in the world of computer experiments and environmental statistics to do these steps, but it's less so common to do this step. FEMA's method, they do this part, but how they do these 2 different parts is something very, very different. So we're kind of combining everything. We're getting this inputs PDF distribution that FEMA does, and also this part that is common in computer experiments. Does that answer your question?
You mentioned at the very beginning that it could be used, like applied to volcanoes. Would it be used like specifically to predict like volcanic eruptions, or like the impact of them?
It would say that if there's a volcanic eruption, what's the height of the lava?
Okay, okay.
So for instance, this one particular island in Hawaii, I read a paper where they wanted to estimate the distribution above 1 meter because that's the limit that they built many of their buildings. So if stuff happens above 1 meter, it can cause considerable problems. Any other questions?
One question. All right, thinker, please.
Went a little bit faster than I wanted to.